Alrighty, 8.8 properties of buffers. As I said here, highlighters or colored writing tools would be handy. You'll see what I mean when we get through the examples. So, we're first going to recap some things that are important for this section. And so, we talked about the common ion effect in this unit before. And so, just to recap that real quick, so if we have a salt, and the salt has the anion of a weak acid, then when it's added to an acid, or the cation of a weak base added to that base, then we can reverse dissociation. AKA, we can make more weak acid because there's too many ions in solution. If we think about Le Chat, if I have too many ions in solution, then I'm going to, well, not I, but the system is going to increase the probably reverse rate depending on how this equilibrium is written. And so you're going to offset those extra ions. And so that's Le Chat, as we've talked about before. And so here's an example of a weak acid, so HF, and it is becoming its ion forms right here. And so if you add NaF, the NaF is a salt, and so the anion of this salt is the F minus. And that F minus is a common ion with the weak acid as stated here. So I'm essentially adding more F minus. Now obviously I'm also adding Na plus, but the Na plus isn't doing anything. It's just going to be a spectator. So we have additional F minus. So that means I have extra F minus in this solution when I add that NaF. And so because I add this NaF, which again is soluble based off the solubility rule you had to memorize, that increases the amount of fluoride ions. So the system needs to use up those extra fluoride ions. And so this reaction is going to increase the reverse rate in order to compensate for the fact it has additional F minus ions. All right. And so when it's reversing the rate, the reverse rate is increasing, that means I'm making more of that weak acid, the HF, that is on the left side. So remember, all this stuff is at equilibrium, right? And so because you added more fluoride ions, that affects equilibrium because it's not at equilibrium anymore, which is why the reverse rate in this particular example is going to increase until you reach equilibrium again. So eventually this system will get at equilibrium where the forward and reverse rates are equal to each other, and then it's good to go. Here's another example with NH3. Cool. And so if I dissolved some ammonium chloride, that means I have additional ammonium ion in there. And so if I have additional ammonium ion, that means I have too much of the product side of this system. And so because I have more of the products, it's going to compensate for that by increasing the reverse rate to make ammonia, the NH3, and then eventually it will reach equilibrium, and then the rates will be the same once it reaches equilibrium once again. Cool. So, buffers. We talked about buffers before in a previous section, but we're going to recap some things and talk about some new things too. So usually we have a weak acid and a conjugate base, as we've mentioned in previous examples. I can also have a weak base and a conjugate acid, and the conjugate is usually in a salt, as I said here. So you have the weak acid plus, for example, like the previous example, actually, right? Like literally right here. We have a weak acid here, HF, and then I can have NaF in the system. And so since this is soluble, you have the conjugate base from that salt. So that would be an example of a buffer. And so, as I said here, here's the example earlier. So the F minus, the fluoride ion, that could be from like sodium fluoride or any other ionic compound with fluoride in it that is soluble. So there we go. And so just like I said earlier, you can have the weak base or conjugate acid. Again, that conjugate acid is usually in a salt. And so with the second example from the previous slide, we have ammonia is the weak base, and ammonium ion is the conjugate base. And so that ammonium is going to be in a salt. So the example we had earlier was ammonium chloride. So that would be the salt. Okay. Here's a tricky MCQ. Which combo is a buffer solution? So I didn't list all the answers here, but one example answer is this one. So just check that answer real quick and then I'll talk about it. Okay, and so the reason why this is a trick answer is because HNO3 is a strong acid. You want to be very, very careful. You have to check if you have a strong acid there because buffers have to be a weak substance with its conjugate. HNO3 is a strong acid, so therefore it would not be a good buffer because it dissociates completely, and so it wouldn't exist as the full molecule itself. So be very mindful of that. It's a very common mistake students make. Cool. Now, again, this example answer choice on an MCQ would be, making sense based off the pattern. You have an acid and its conjugate in a salt. But again, because this is a strong acid, you want to be very careful because, again, strong acids aren't good for buffers. As a reminder, the reason why we learned about buffers is to resist pH change. We're trying to not change pH, or the buffer is trying to not. So, for example, in our bloodstream. So in our bloodstream, we actually have a buffer system, one of them anyway, is carbonic acid and bicarbonate ion. The blood is mostly water, so mostly aqueous stuff. And blood doesn't really want to change pH that much because otherwise your body would be kind of jacked up. And so let's think of a hypothetical, okay? So let's say somehow soda got into your bloodstream. And soda is hella acidic, like super acidic. It's actually not great to drink. And so if that soda somehow went into your bloodstream, then the buffer system, it was carbonic acid and bicarbonate, is helping prevent that blood from not changing pH significantly. So it'll change a little bit, because we saw the titration curves where the pH does change a little bit for adding any acid or base in the solution, but the buffers help it not change that much. And so blood pH is around like 7.4-ish. And so if there was somehow, again, soda added into the bloodstream, it wouldn't change that much. It might change to like 7.2 or 7 points. Yeah, we're going acidic because it's acidic. Yeah, so it'd be like 7.2 or 7.1 or something. Okay. Now teeth. Your teeth don't have a buffer system like blood. So when you drink soda, if you consistently drink it every day, for example, you're slowly eroding the enamel, potentially. I mean, obviously, if you're taking care of your teeth well and you make sure to not have soda in it too often, like it's fine to have as a treat every now and then. Enamel doesn't have living cells. So once your enamel is jacked up, it's pretty much donezo. You can obviously get implants and whatever else, but then you have to replace those every once in a while, so you want to be careful about what you're consuming. Again, soda is very acidic, so since we don't have a buffer system in our teeth, then you are eroding your teeth. Yeah. So pretty much buffers are keeping you alive, for the most part, like I said, with the bloodstream or any other biochemical reactions that are happening in your body, and without them, we wouldn't be alive. So, cool. All right. So, we're going to talk about different buffer systems. We're going to talk about a weak acid buffer system. And in this weak acid buffer system, we're going to add a strong acid. Now, when I go over these examples, you want to make sure to understand the process of why we're doing this. Because I'm trying to logically tell you how I'm getting all this information from this problem. So we're actually going to go through each of these parts. So our weak acid buffer system, we have our weak acid here is HF, and then we have its conjugate base, NaF, because remember the F minus in this salt is the conjugate base. And so we're adding a strong acid, which is hydrochloric acid. Okay? And so we're going to list the major species that exists in this system. So we have the buffer system, and we're adding an additional SA, the hydrochloric acid again. Okay, so we have the hydrochloric acid first, because I'll just focus on that. And we know it dissociates completely. So because it dissociates completely, we're going to have the ions, H plus. So let's write that down, so H plus. And then we also have Cl minus. Now as a reminder, H plus doesn't exist. It's technically hydronium, H3O plus, but I'm just going to write H plus for the sake of this. Okay. And so that's one of the major species, or two of the major species, H plus and Cl minus. The next one is HF, and it is a weak acid. So technically it ionizes a little bit, but for the sake of this example, it's a weak acid, so I'm going to stick to it mainly focused as the molecule intact. So again, a little bit dissociates, but not too much. So I'm just going to keep it together. Then we have the NAF, and because of the solubility rule that you had to memorize, NAF dissolves completely. So the species from the salt is going to be Na plus and F minus. Cool. And then, of course, this is in solution. So because it's in solution, we have water. And so water, I'm just going to literally write water. And so there we go. So those are our different species in this system. Now, water technically autoionizes, but we're not going to focus on that because that is too much. We're focusing on the main players of this system, and so I'm only looking at the main players. Again, autoionization does happen with water, but we're not going to hardcore focus on that much. Okay, so now that we have our major species in this buffer system, we're going to look, we're going to look at what is actually neutralizing, okay? And so we need to figure that out by looking at the different species. Okay, so when this neutralization process is happening in the system, as a reminder, the buffer system is trying to resist the pH change. So when you're adding a strong acid without a buffer, the pH would change significantly. So the pH would drop hello, because pH, again, if you have a low pH, the lower, the more acidic. And so we're trying to compensate for that. And so the buffer's components are the ones that should be neutralizing this acid. So when we're thinking about these species, which species is the major, aka the strongest acid? So the one that's for sure giving away the H, okay? And so I'm going to look at our different acid options in the list of species. So we have our H plus over here. We have our water. And then we have our weak acid, right? So those are our three options for acid. So let's go over each of these choices. So HF is weak. So it's not going to give that H much. So it's the HF is not really affecting the pH right now. And then water, yes, it autoionizes, but not significantly giving that H that much. So water pretty much sticks as water most of the time. So the thing we need to neutralize is the H plus from the strong acid. Again, that H plus, which is the hydronium technically. And so this is what we're looking to neutralize. So looking to neutralize, we're looking to neutralize that H plus. Alrighty, so next we are looking at what can accept an H. So I would use a different color, but you have to pay for that. I'm not about to pay for that. So we are looking for the thing that can accept an H, aka the base. So what are our base options? We have our chloride ion here. We have our F minus here. And then we also have our H2O. So that is our base options. Now, which one will actually be the base in this situation? It's kind of hard to choose from looking at this, just looking at this. You could logic it out, which I will do, but I'm also going to write down some explanations because I think the explanations are really important on why we would choose certain choices but not the others. So let's think about this chloride ion, right? So we're trying to neutralize the H plus. So if I write down the hypothetical neutralization. That would be it. And we can't form HCl because HCl is a strong acid. So since it's a strong acid, HCl is always dissociating, so that cannot be the correct choice. We also have the water. And so the water in the system could technically be H3O+, right? And hydronium. And hydronium is not particularly strong. It's not too weak, but it's not too strong. It's still like decently weak. And water autoionizes, so there's already H3O pluses in there. So it's kind of like a neutral answer, so that doesn't make sense. And so if I'm looking at the fluoride ion, so the H plus and the fluoride ion, bam. And HF is definitely a weak acid because it's not part of the strong acid list. And so weak acids want to stick together. So the F minus, the conjugate base of HF, is going to act like a base pretty well compared to our other three options. So our F minus here is going to be our choice for neutralizing. And so pretty much we're going to use that fluoride to neutralize. So H plus F minus is making HF. So we're making a weak acid. So that's how we would go through these problems. We're adding something specific in the system. We're looking at the buffer and how it reacts with whatever you're adding. And you're seeing what part of the buffer is being used. So in this case, we added a strong acid, the hydrochloric acid. So we're dealing with the H plus because that's the part that's going to be affecting this buffer the most. And in order to neutralize some of that H plus, the salt has the conjugate base, so the NAF. And so the F minus, the fluoride ion, is going to interact with the H plus in order to neutralize. Okay, so that is how we would do this problem. So here is the next example. So I have it here. I also have this little picture here, and I'm going to use that picture to talk about electronegativity. So we're going to talk about that in this example. So we're going to list out the major species. I'm not going to do it the same exact way as the previous example just because I don't need to go through every single one. So we're going to go ahead and do this. So this is a weak buffer system. So we have a weak buffer here, and then we have the conjugate acid here in the salt because the NH4 is the conjugate acid. And so let's talk about our major species. We have water because this is all aqueous. We have the strong acid, so strong acid dissociates completely, so we have those ions. And then we have the weak base, which is the NH3. And then we have the salt, which has the conjugate acid. And then we also have the chloride ion, also from there. So notice I listed chloride twice. It's fine. Whatever. And so our acid choices. So our acid choices, we have the H+, we have the water, and then we have the ammonium. So those are our acid choices. The strongest acid is literally the H plus from the fact that we added HCl. So that is going to be the one we need to neutralize because it's from the strong acid. And so that's why I wrote it here. So I'm going to go ahead and erase those check marks. And so this is when I would use another color. Oh, I could use highlight maybe. Can I use highlight? Oh, I could. Okay, well, next time. So now we're going to look at our base choices. So our base choices are water and the chloride ion and the ammonia. Cool. And so chloride can't be it because if I add a H to Cl, it's going to make HCl, so that makes a strong acid, so that can't be the correct one. So I eliminate that right away because it's strong. And so now we have water and ammonia. Now, they're both pretty weak in terms of weak bases, so we need to think about which one would be the thing that's actually neutralizing the system. Now, the reason why I'm going to pick the choice that I pick is based off electronegativity. So If we're looking at water versus ammonia, there are, again, those two choices because they could both act like a base. And when I look at the Lewis diagrams for the water and the ammonia, we're looking at the central atom mainly. So we're in this case, we're looking at the, let's highlight it. We're looking at the oxygen over here versus the nitrogen over here. And so we're looking at the electronegativity of these. So remember, it increases going left to right. So we notice that nitrogen is less electronegative compared to oxygen. And so the N is less strongly holding electrons compared to oxygen. Because again, electronegativity is about how strong the electrons want to stay with that atom. And so because N is less strong compared to oxygen, then it is a better electron donor. AKA, we can add H plus to it to be more stable compared to hydronium. So this ammonium is more stable compared to this guy. And so the electrons attracted to the atom, again, oxygen attracting to the H versus N attracting to the H. If we're ignoring like the bonded pair, we're literally thinking about the H plus literally as a proton, it's going to be shared unevenly. Oxygen doesn't want to share as much as nitrogen, and so the reason our choice is ammonia is because of the electronegativity of N versus O. So in this case, this is our better option for neutralizing, so that's going to be our NH3, and then that would make our NH4 plus. So it's going to make our conjugate acid. Cool. So careful about that. I mean, it's in retrospect, it's kind of easy to figure these out without writing the major species because you just look at the buffer systems, like what part of the buffer is affecting it. But it is good to know the different species in the buffer system when you're adding something to it, and then you'll see like the effects of that. Cool. All right. Okay. So here is our next example. So we have a weak acid buffer system. We're adding a strong base. So in this example, it's going to be similar to what we've done before, listing the major species and then looking for the neutralization. So try this out first. List the major species that are in this system and then see if you can know which ones are the acidic choice, which ones are the base choice, and then from there, we're going to make the neutralization happen. So go ahead and pause this video and try it out yourself. All right, ready? Species, let's do it. So we have our water, because this is all in solution. We have our strong base, so that is completely ionized. Then we have our NH3, and then we have our salt that is dissolved. There. So let's look at our acid choices. So our acid choices are water and ammonium. And so I could talk about the same situation as the previous example on why it's going to be NH4 that could deal with the strong base. So it's going to be the NH4 that is going to deal with that. And so cool. And so then we're looking at our base options. So our base options are water. We could do the hydroxide, the NH3. And so what are we trying to neutralize? We're trying to neutralize this strong one. So the strong one being OH minus. And so we're going to go ahead and write that in our neutralization. And so when we're neutralizing this, our H is going to be donated to the hydroxide. So this is the conjugate acid. And so it's becoming NH3 plus water. Because again, the H is being donated to that water. Cool. So You should be able to determine the reaction that's actually happening in the system when you have a buffer and you're adding whatever you're adding. Now, as I said here, you do not need to go through the process I went over in these examples. These are examples just to clearly show why I'm listing certain species, what's actually in the system, who's interacting with who. So you can do this all in your head if you understand the concepts of how buffers work. Just be able, you should be able to explain what is happening in an FRQ type problem. Like, why is this thing the one neutralizing the strong acid, for example, or why is this thing neutralizing the strong base, for example. So here is a your turn, and this is how it would look potentially on an FRQ or MCQ. So go ahead and look at these and then try them out by pausing the video. Okay, ready? Here we go. Answers. Bam. Bam. Those are our answers. Again, you did not have to go through the process of the examples we did before. It's just a good idea so you don't get lost in the sauce on what we are doing. Alrighty, that is it for this section. Bye!